Hi, good morning. So I'm Chris Bailey, and myself and Robert Dickerson, we work for the Swift IBM engineering team. And this morning, we're going to talk to you about building end-to-end applications in Swift. Now, as part of that talk, we're going to try and achieve two things. First of all, explain why Swift is actually a very good language to be using on the server as well as the client. And secondly, and hopefully more importantly and more interestingly, give you a real example of an application that we've built that does that and show you how to achieve that yourself. So the first thing is modern application design for end-to-end applications. So you have an end user who is going to be building a client-facing application, which, given that you're here at Swift New York, I'm assuming you're going to be doing in Swift. Then you're probably, at the moment, creating some kind of back-end application service and doing that using Java or Node.js or Ruby or one of those kinds of languages. That, in turn, is probably going to be using some kind of third-party services, whether that's Elasticsearch or Twitter or Twilio or OAuth or some kind of NoSQL database. And you might also be using some kind of legacy database on an on-premise system, so DB2 or Oracle or MySQL. So what we're going to try and convince you is that rather than just using Swift for your user-facing client apps, you should also be taking Swift and using it on the server, which gives you an integrated developer experience. So you can use the same IDE and share code between client and server. So that's great, but why Swift on the server? What's the advantage of actually using Swift on the server? Well, one of the things is it's actually really quite highly performant. So this is taken from a set of public benchmarks run by a group called Alioth that run the benchmarks game. And these benchmarks are run across a whole number of languages. They run them on Linux on a 4-CPU machine. This particular benchmark is called Spectral Norm. It's just mathematical number crunching. So it tries to burn all of the available CPU. And the benchmark in this case uses dispatch and runs on all 4 available CPUs on the machine. Now, Swift completes that task in 4 seconds. Java does it in just about the same time, in 4.3 seconds. So Swift and Java's performance on a 4-way Linux box for this task is actually almost identical. You then look at something like Node.js. So Node.js takes 15.8 seconds. So it's actually roughly 4 times slower than running Swift or Java. And if you run something like Ruby, then it's incredibly slow. Right? Ruby is not a language for doing computation, largely because it doesn't have a form of just-in-time compiler under it like Node.js and Java does. So for performance reasons, Swift's actually a really interesting language to be running on the server. But it's also really good for memory. So looking at exactly the same benchmark and looking at the resident set size, the amount of physical memory that's needed to run that benchmark, Swift requires 15 megabytes worth of memory. Java, however, requires 32. So you're running in half the amount of memory but getting the same performance. Node.js needs a little bit less than Java, but it's still a lot more than Swift. And again, Ruby requires quite a lot. Now, this is interesting because if you actually run applications in a cloud, most clouds actually charge you by memory usage. So you will buy a 256 meg container or a 512 meg container, and the CPU actually comes for free there. So what this means is Swift is actually an ideal language to be running in the cloud, because it's both highly performant and low memory footprint. So you can get more containers for the same amount of money and therefore run more instances of your application. So it's good for the cloud, so it's good on the server. It's also good for developers because of what's loosely called isomorphic development. So the idea here is you are a developer and you're building your Swift project. And you can create a project that has both client and server components to it. And you can build that in the same project, and you can write it in the same code. In fact, you can share components. And then you can deploy that application both onto the client and onto the server and have connectors for whatever databases or data stores it needs. And at the same time, you can almost certainly generate a Swagger-defined API that sits in the middle, because you might want clients that, you might want a browser client or an Android client for it as well. But as your first-class citizen, you've created a Swift application on both client and server. And this has the side effect that, of course, you get to use the same tools, so you can use Xcode for everything. You can use the same build systems. You can use the same linting infrastructure. You get to use the same tools and technologies everywhere. So what does it take to actually be able to do this? So how do we get Swift running on the server? So the first thing we have to do is actually make the language run there. Now, when Swift became open source in December last year, on Linux, it wasn't complete, shall we say. We had the Swift runtime, we had the standard library, we had a little bit of foundation, and we had a version of dispatch, but it didn't actually really compile, and it certainly didn't pass any of the tests. Where we are now is that we have a working version of foundation, and we have a fully working version of dispatch, and those are both in the Swift 3 toolchain, and they're going to be in Swift 3 GA when that goes out next month. So that now gives us consistent platform between client and server. The next thing you need, of course, is a web framework, and IBM's been working on called Kitura. There's a whole number of other ones out there. Tanner Nelson's around here somewhere. He's been working on Vapor. So you take your two platforms, and then you add a couple of necessary things in order to be able to run server-side code. So the first thing you need is networking. You also need security if you're going to do HTTPS and secure WebSockets, and you need some form of HTTP parsing. So we've added 3 additional libraries to do that. We've then added our web framework, and once you start writing your client application, you can then actually start to take application libraries used by your application and use them on both sides. So you can use them in the client, and you can use them on the server. So that's great. But one of the things we've been trying to do with Kitura is to use standard components. So we use dispatch for concurrency. And the reason we do this is because both it's the right thing to do because it's a good library, but secondly, when we find a performance problem and we fix it in dispatch, the rest of the community inherits that. When someone else finds a problem in dispatch, we gain from that as well. So the more users there are of a given component or a given library, the more sharing there is, the higher quality it becomes, and everybody benefits. So as part of that drive to use standard components, we've been working with Apple and some other people in the community for the last couple of months to put together some work that we're trying to do to take those 3 components in gray and make them standard components. So make them as part of the Swift runtime and create a set of server API components. And you're going to hear more about this in the next few weeks when it actually formalizes and starts to get underway. So between those two, between Swift 3.0 being a solid delivery of Swift on the server, plus web frameworks like Kitura, we now have Swift on the server as a real option for deploying the back end for your iOS applications, with all of the benefits of being able to share code. So now I'm going to hand over to my colleague, Robert, who's actually going to show you how to do that for an application.
So in this example, we're going to build a social networking backend with Swift 3. And this is a kind of a typical backend application, standing up a HTTP server, create a router, which is basically just a way of taking an incoming request, applying, matching some kind of regular expression on it, and routing it to the appropriate handler. If you're already a Node.js or Sinatra or Flask developer, all this is kind of natural to you. We can also plug in various different middleware. So for instance, we've built a Facebook's credential middleware that you can plug in, and it can intercept the request, validate the OAuth token, and get you back a username for the user. I'll show you an example of doing that in a second. And we have various different handlers here, which are basically closures that are invoked when that router finds a match. And then we're going to use a Cassandra backend because it's a very performant database, and we hadn't worked with Cassandra yet. So The steps are I'm going to show you how to set up the project and the dependencies, set up the routes, add the Facebook authentication, set up the model in the database, and handle the requests. Since many of you probably haven't played around with Swift 3 on the command line yet, I want to show you just an example of what happens when you install Xcode Beta 8 or the Swift toolchains on Linux. If you create a new directory, you can use the Swift package manager to say Swift package init, and it creates some boilerplate code for you. So you're already ready to get started. It's kind of like npm init. And we can generate both the sources, which is basically a hello world app, and then a test scaffolding, so you can add your test cases here. I've written code in Emacs on my Linux machine, but also on a Raspberry Pi. But probably most of you will want to develop in Xcode, and you can transform that package.swift file in that project into an Xcode project by using Swift Package Manager with the generate Xcode proj command. And you have the Xcode project. I really love developing in Xcode when I build back-end code because I can step through the code, I can add breakpoints just like I'm used to in Xcode, I have type checking, I have code coverage, I have profiling, all those tools work on back-end Swift. We're going to add some dependencies here in this project. Your package.swift file is your way of specifying dependencies. You don't have to work with Carthage or CocoaPods anymore. You can specify the GitHub URL and the major and minor version that was tagged on those repositories, and the Swift Package Manager will automatically download those dependencies in. Next, how do you set up routes? So if you are used to Express.js or Sinatra, we use a very similar syntax that you can register update requests on gets or posts or puts and deletes. And you get back a request response object and also a function you can call to hand it off to the next set of middleware. If you want to pass in URL parameters, you can parameterize that using the colon user here, and then I'm fetching the user later in the parameters. Usually I like to encapsulate all of that logic into a controller. So here I've produced the Blitter controller class, created the database driver, the router, and then register all those routes inside of my constructor. So how do we add Facebook authentication to this? Here we have the credentials module. We just create the credentials and then go ahead and plug in the Facebook credentials into our middleware. We also have support for GitHub and some other authentication sources. So if you want the middleware to intercept the traffic, you register the credentials middleware on that route. For instance, when I want to post as an author a new bleat, I will post at the root path, and then the middleware will check to see what my username is, and then that will be my user that's used. Okay, setting up the model in the database. So a bleat is basically an ID, the author, the subscriber. So for every time I write a bleat, all of my followers get a copy of those bleats. So that's how we're going to structure the data here, the message of the bleat and then the post date. And the key is that we're using Foundation here, which is really nice. Notice that you don't have to do NS anymore. That's been renamed. So using the date and UUID is fine here on Linux as well. Since when you're writing backend code, you often have to structure things as JSON quite a bit. So it's useful to have some notion of converting a structure into a string value pair. So here we define a protocol for making sure that that conversion is possible. And it also makes sense that if an object is string value convertible, then a collection of those should return a collection of string value pair convertibles as well. So if we wanted to go ahead and make this so that we can easily turn this into JSON, we can define a bleat with this kind of string value pair conversion. method. Okay, so how do we take that existing structure and then give it the ability to be persisted or saved into the database? By using the Cassandra driver that we developed and by extending the capability of the bleat with the model behaviors, then we could just specify the name of the table where bleats are stored, and you have a lot of persistence functions for free. For instance, when I create a new bleat, I can go ahead and create a new one and then connect to the database and just call save on the object. So it's very simple for persisting the data. Let's say that you have a list of strings of subscribers and you want to create a new bleat for each of them and then save it to the database. Well, you can map the subscribers list onto the constructor of the bleats, and now you get a new list back, and then you can call save on it. And I do realize you can chain the for each at the end of the map function, and all of this could be one line of code. So for asynchronous error handling, oftentimes you'll see APIs give you back either the value or the error, and there's this sort of mutual exclusion between the two of them. So I recommend that you go ahead and exploit some of the properties of the language in order to ensure that mutual exclusion. And thanks, Rob, for your talk yesterday, the Lambda talk, where you mentioned doing something like this, where you have an enumeration of the result, which is generic, and it could be success with the object that you're interested in, or an error. And if you want to get the value back, then it either returns nil if there was an error, or the value back. Okay, so how do we get a list of bleats back? We can connect to the database. We fetch all the bleats. If there's an error, then we call the onComplete with the error case. If you are able to get some results back, then you go ahead and create bleats out of them, and then call the success handler, the success case here. We can also handle predicates too. So if you just want to get bleats back that match a certain author name, we can exploit some of the operator overloading properties that Swift has, which is great, where that double equals now gets evaluated as a predicate clause that can be applied in our query. So here we get back only those that match an author, and it's limited to just 50. Okay, and then finally I want to show you how to handle the requests. So when we get this bleats back, we have a result. We check to see if that result was a success. If not, then we can go ahead and append a bad request to the response type. So that's basically a 500 error. And if it was successful, then it's a 200 status code. So that's how we set those status codes using the status method here. And then when you're ready to serialize the JSON, you can do a .send with the JSON. We already set the MIME type for you for the JSON type. And we use that string value pairs to get us back that dictionary. And using Swifty.json, that dictionary will be turned into a JSON object and serialized as a string. Okay. Oftentimes when a person will post a message up to the web server, it will be in the form of JSON, and we want to be able to extract some information from that JSON. So in this case, we can extend the router request object, checking to see if there is a body in the document, whether there's JSON, and then going ahead and returning that JSON. When we're ready to save the bleat, then we can go ahead and get the message from the JSON and save it. Okay, so I encourage you to look at our code. I went really fast through these slides, and my slides are also up at that repository. So definitely check that out. If you're also interested in other examples of using Kitura, we've built a to-do list app in multiple databases. So a lot of things like MongoDB and Redis, we've implemented a to-do list for. And we also have a corresponding iOS app. If you're also interested in a more extended example that uses AngularJS, we have a Bluepick web example that uses a Kitura backend, CouchDB object storage, and Watson too. And we have both an iOS front end and an AngularJS front end. So check out that repository if you want to see some examples there. So thank you very much. That's it for me. Hope you download Xcode Beta 8, Xcode 8 Beta, and the latest toolchain and play around with Kitura. Thank you.